Hi, I'm Tushar Swamy, and I will be presenting our work Taurus, a data plane architecture for PerPacket machine learning. So this is a quote from a 2015 Google blog, and at that time Google was already dealing with more than 1 petabit per second of bisection bandwidth, and their networks and data center networks in general have only continued to grow. As a result, they're getting harder and harder to manage, and these networks require more and more complex management while maintaining high performance. Machine learning can actually serve as a good system to scale complex management in networks. An ML model can take in data and train a model to make progressively more accurate decisions, and they can approximate network functions where the analytical solution is too complex or slow. And in addition to that, machine learning will also customize its function to the data it sees, and in turn customize itself to the network in which it operates. And both of these things are already happening with network functions in the form of hand-tuned heuristics like hashing and load balancing, and TCP congestion control algorithms with operator-tuned parameters. So why not scale the process by automating it with machine learning? If we want to add machine learning into the network, we need to figure out the best place for it to live. In a typical software-defined network, the network is split into the data plane, which is responsible for packet forwarding via the match action abstraction, and the control plane, which is responsible for policy creation through flow rules, which dictate how the data plane should handle packets. So where exactly does ML fit in here? Taurus introduces machine learning into the network by splitting ML training into the control plane and ML inference to the data plane. In a Taurus network, the control plane can create policies by training models in addition to flow rules and installing the model weights into the data plane. One of the core tenets of Taurus is that ML inference should happen per packet in the network data plane. And to see why, let's take a look at a quick example. In anomaly detection, we're trying to distinguish between malicious and benign packets. And in this example, the network is running an anomaly detection application in the control plane. When an anomalous packet is found, the control plane will install a flow rule to deny further packets with a similar signature. So let's say we have 1 gigapacket per second of malicious traffic entering the network. Let's just make the calculations easier. And in the top left corner here, we will keep track of the processing time needed to identify the malicious packets, and then the packets missed during this processing time. So as the first packet of our malicious traffic stream enters the data plane, a packet digest is going to be sent to the control plane. Let's say that takes half a millisecond, and in that time, we've already missed 500,000 packets. Let's say the control plane takes another half a millisecond to detect or identify any anomalous elements of the packet, and we've missed another 500,000 packets, so we've missed 1 million total so far. And now the control plane needs to install a flow rule into the data plane for further detection of similar anomalous packets. And in this time, we've missed now 1.5 million packets. So you can see that if we get the control plane involved, we introduce too much transit time. In addition, the data plane must process each packet as it arrives, so whatever decision making can be applied to each packet. In this example, anomaly detection needs to be applied per packet, or else it risks letting malicious packets into the network. So overall, this is why we say that when we're doing machine learning inference, that's the decision-making portion, we want to do it on a per packet basis at line rate. In a nutshell, we can say the robustness and performance of our network is determined by the quality and speed of reaction. The quality is determined by the training data that would go to our machine learning model, and the speed is determined by line rate operation and the granularity of the response. So again, in our Taurus network, we split up our training and inference processes, and the ML training is going to happen off the critical path. So we can let it live in the control plane. And in that control plane, we can train models and use different ML accelerators. The control plane can take state and telemetry data from the network and retrain and update these models. ML inference, however, is again the decision-making process, and so that has to happen on the critical path, or the packet forwarding path. So the outstanding question here is, how do we build a data plane to perform ML inference at the speeds required by a data center network's data plane? And this is exactly what Taurus is built to do. Taurus itself is an architecture for per-packet machine learning inference in the data plane. To build Taurus, we began with the typical programmable switch pipeline. Programmable switches today have several structures for tasks like packet parsing, network functions via match action tables, and scheduling. The protocol-independent switch architecture, or PISA, is a common implementation that has all these elements, and we use that as a starting point for Taurus. If we want to introduce hardware into this pipeline, we need to discuss what abstraction is appropriate. In Taurus, we use the MapReduce patterns. MapReduce is a commonly used abstraction for ML. It supports common linear algebra operations found in a variety of ML algorithms, such as neural networks, support vector machines, and k-means. In addition, it's a SIMD pattern, so it allows for a lot of parallelism with very minimal logic. It also allows us to perform unrolling. Unrolling patterns allows for flexibility as far as resource usage is concerned. And for those who don't know, unrolling here means that in the case of a loop, we can execute loop iterations in parallel. And more unrolling leads to better performance with more resource usage, while less unrolling leads to less resource usage, but at the cost of performance. And so you can see in the picture here on the right, we show how a neuron in a DNN could be implemented using the MapReduce abstraction. So map is a pattern that takes two vectors and applies an element-wise operation across it, while reduce combines the elements of a vector into a scalar. So in the blue block, map is used to perform element-wise multiplication between the inputs and weights, while the reduction then takes the resulting vector and it combines it along with the bias into a single scalar value and it does this through addition. And finally, it applies an activation function across the result. And so that's how you would do a single neuron, but you can imagine that you can stack this pattern across multiple neurons in a layer, and then you could map the activation functions as well. So to build Taurus, we keep the majority of the piece of pipeline, but we add a MapReduce unit to execute ML inference. The match action tables are split into two blocks around the MapReduce unit for pre- and post-processing of ML inputs and outputs, while the packet parser is used for ML feature extraction in addition to its typical duties of header extraction. So we had some requirements to build our MapReduce unit. You can't just drop an ML accelerator into the pipeline. The MapReduce unit has to be reconfigurable, so it can be programmed for different applications and tasks. It needs to meet line rate with a fixed clock, so it can keep up with other elements of the PISA pipeline. And the fixed clock here means that we can't use an FPGA. And finally, the hardware that we add in should incur minimal area and power overhead. As a final challenge, most accelerators are built for batched processing, but in a network scenario, we have to process packets as they enter the pipeline, which is a batch size of 1. So to make this a little more concrete, let's go back to our anomaly detection application and see how a Taurus pipeline might actually handle this in practice. So here we have a picture of our data plane pipeline. and a packet's going to enter the pipeline. It first enters the packet parser, where we're going to do our header and feature extraction. So it's reading local features, say an IP address. The packet then moves to the pre-processing block of match action tables, and this is where we're going to do our data augmentation, integration, and cleaning. And in this case, maybe we're retrieving some out-of-network events that were installed by the control plane, something like the number of failed logins per IP. The packet then moves to our MapReduce unit, where we apply our learned anomaly detection model. Say it's a deep neural network or support vector machine-based model in this case. And it's going to give us an output between 0 and 1, where, say, 1 means that the packet is definitely anomalous, while 0 means that it's a benign packet. The packet moves to the post-processing block of match action tables, and this is where we do interpretation of whatever score the MapReduce unit has given to the packet. So maybe we drop the packet if it has a score of 1, because that means it's anomalous. And then finally, the traffic manager just makes sure the packet gets to its destination. In order to evaluate our design, we go through the ASIC synthesis process for our MapReduce unit. Our evaluation platform for the MapReduce unit is based on plasticine, a reconfigurable data flow architecture, and it's programmed with Spatial, a hardware description language that allows us to write our apps with map and reduce primitives. In the vein of plasticine, the MapReduce unit is built from a grid of compute and memory units, where the compute units are built from SIMD lanes and memory units are built from blocks of SRAM. We had to make a number of changes to the original architecture, though, to allow it to run at line rate in a network. We strip out the floating point units and modify the number of SIMD lanes and pipeline stages within the compute units. In addition, we had to remove any manner of accessing off-chip memory because DRAM accesses would be too slow for line rate. In the evaluation of our ASIC design, we use a 12 by 10 MapReduce grid and compare it to a 500 square millimeter switching chip with 4 pipelines, and this is typical of top-of-the-line switching chips. This is sufficient to support our entire benchmark suite of real-world applications. We find that in order to add a MapReduce grid to each of the pipelines, we only add a 3.8% overhead to the overall switching chip area. And really the takeaway here is that we can enable a whole class of applications for pretty minimal overhead. One of our benchmark applications is actually our trusty anomaly detection application, and we've implemented it with 2 different algorithms, support vector machines and deep neural networks. Both are trained on the KDD dataset of network attacks, and the SVM model has 8 support vectors and the DNN has 4 layers with 12, 6, 3, and 2 neurons. We can see that for both models, the throughput is 1 gigapacket per second, which is typical of high-end switch pipelines, as well as latencies in the hundreds of nanoseconds or less. And so you can choose your exact model implementation based on your latency constraints. For area and power, both models have overheads of 1% or less, and this continues this theme of application flexibility for very minimal overhead. And finally, we don't want people to wait for some sort of Taurus ASIC to be mass-produced before writing their own ML data plane applications, and so to this end, we've made an open-source FPGA-based Taurus testbed to allow people to try their own ML for networking apps. We use an FPGA to emulate the MapReduce block, while a Tofino-based switch serves as the PISA elements of the pipeline. In our repository, we've also included the code for the anomaly detection application to help people get started. I'm happy to take any questions. I have left my contact information here if anyone wants to discuss further, and I also have a link here to our GitLab testbed repository that people can use to start running their own data plane ML applications.